So far, we've been focusing on streams largely from a logical perspective, kind of showing how information is transformed as it flows from one operation to the next. We're now going to talk about some of the key things that are themes that will show up here shortly in this course, which are transforming from sequential streams, which is the default, to parallel streams. Since, of course, this is a course on parallel functional programming, that's going to be important. So I'm going to compare and contrast sequential and parallel streams, and also try to get across the key point that a parallel stream is very simple to create once you understand how to program a sequential stream. So by default, streams run sequentially, and that's what we're going to focus on here first. We'll do a bit more today and maybe next time as well. And the reason why we're doing the sequential streams first is that's where all the interesting stuff shows up with respect to these different types of operations, intermediate, terminal, factory methods, and so on. But the good news is once you understand sequential streams, as we'll see, it's trivial to convert from a sequential stream to a parallel stream. You get a sequential stream by using the .stream factory method. There are other ways to get a stream as well. And the .stream factory method is used on a collection to convert a collection, like a list, into a stream. There's other ways of doing things too, like of, we've talked about as well. And then not too far from now, maybe starting next time or the time after that, we'll start talking about parallel streams. And you'll see that parallel streams have very, very similar look and feel in terms of their structure and functionality to sequential streams, the main difference being that, of course, the operations in the stream can run in parallel. And there's hopefully good motivation for that, because then you can get speed-ups. And we'll show an example of a speed-up here in a second. A parallel stream splits its data, the data it's working on, the data it gets from the factory methods, into multiple chunks, and then uses the common fork-join pool to process these chunks independently. If you recall, we talked about fork-join pools earlier. I mentioned how they were an object-oriented feature, an object-oriented, fine-grained data parallelism engine that was introduced in Java 7. And so there's something called the common fork-join pool, which is just a singleton fork-join pool that always exists in Java programs. And we're going to talk a lot about how the common fork-join pool is used in conjunction with parallel streams and completable futures, for that matter, in order to be able to actually do the underlying processing. And so the fork-join pool is actually what runs the computations, but the stream and the parallel stream is a functional wrapper that encapsulates the fork-join pool, because the fork-join pool is a little bit awkward to program directly, whereas streams are a much more convenient programming abstraction. In the fork-join pool, there's a bunch of worker threads. These are actual good old Java threads, what we would now call platform threads with Project Loom model of Java. And each of those threads runs a loop that continuously scans for tasks or subtasks to execute. And we'll talk more about this, how that works, when we get into the parallel streams discussions. You'll get a better view of how things work under the hood. But for now, just think of it as a bunch of threads that are out there running, looking for work to do. And the goal in the fork-join pool, and parallel streams for that matter, is to keep things humming along and keep the worker threads as busy as possible. The goal is to maximize utilization of the underlying processor cores. And the way it does this is by using something called a work stealing algorithm. And you can read about the data structure for work stealing called the work stealing deck, which stands for double-ended queue, at this link at my website. And basically, to summarize something I mentioned before, every worker thread in the fork-join pool has a deck of tasks or subtasks that it's going to be working on. So think of it like its work queue. And in fact, that's what it's called. It's called its work queue. And the way that it works is that a thread in the worker pool, thread pool, will keep checking its work queue to see what it needs to do next. And as long as there's work in its work queue, it dequeues the work or pops the queue off the top and takes it and does something with it. However, if a thread happens to run out of work in its deck, if it's not playing with a full deck, as we say, if it's playing with an empty deck, then what it'll do is it'll reach around and find another work queue by randomly querying the queues, and it will then go and try to steal work from the end of that queue. And the idea there is to keep things, again, humming along, maximizing utilization as much as possible. And this is a very cool approach, and we'll talk about this a bit more when we get into the nuts and bolts of the fork-join pool. So why do we do all this? What's the reason for this? Well, the reason is we can get a speed up often depending on various circumstances. So as we'll see, a parallel stream can often be much more efficient and scalable than a plain old sequential stream. And this particular example, which is something we may have a chance to look at later, it's called the Search Stream Gang program. And this is the results of this program run on my MacBook Pro, this little computer here. And it illustrates nicely the benefits of using streams and parallel streams. So first of all, these are just a bunch of different implementations that all do the same thing. They all search for phrases in the complete works of William Shakespeare, which is pretty cool. But the key thing to note here is the improvements relative to the sequential versions when we start turning on different parallelism models. And in particular, if we run this program with the sequential streams enabled, that's the performance. It takes about 2,500 milliseconds to do all the searching to find the phrases in the works of Shakespeare. But when we turn on parallelism, we get a very, very big speed up. And the differences between the parallel versions are probably not that significant, but the main thing to notice is they're much, much faster than the sequential version. So the different parallel streams implementations all do much better. And the reason for that, of course, is because they're taking advantage of the underlying processor cores. I got 10 cores. Now, we're not seeing a total linear speed up, but it's doing pretty well. Another thing to note, which is just kind of fun, is that the performance of a sequential implementation that just uses good old Java 7 style loops and if statements is indeed faster than the sequential streams version. So the takeaway from that is there is some overhead of using the streams abstraction. However, the good news is that by leveraging parallel streams, which as we'll see is as easy in many cases as just saying dot parallel stream instead of dot stream, we get this massive speed up in performance. So that's one of the benefits of using a higher level abstraction like streams, is it becomes much easier to scale the solution without having to do a lot of extra work. And we'll talk about some of these other implementations at other points. So here's the question. The question is, are there any impediments or slowdowns or sources of overhead incurred by the use of parallelism in this model because of the way in which the different steps have to work? So you filter something and then you capitalize it. And the answer is no. And the reason for that is that all the operations that are done here in this particular program are all stateless operations. And when they're stateless operations, there's no dependencies between anything. There's no state that has to be managed. There's no shared state to be read or written to, which means that this particular type of program is what's known as embarrassingly parallel. So all the operations can actually indeed run in parallel. And when we get to talk a bit more about how parallel streams actually works under the hood, you'll see that they do a very clever thing so that what it does, not to give away too much of the suspense that we'll talk about later, when a source of data, like let's say we take, depending on this thing, this is taking the phrases. So in this case, each of the phrases that we're searching for, like, to thine own self be true, or out, damn spot. Think of your favorite Shakespeare play, quote. So each of the phrases is running in parallel. And so for every phrase, it'll then go and look through all the works of Shakespeare to figure out whether that phrase occurs in any of the works of Shakespeare. And so that computation can run completely in parallel with no dependencies, with no conflicts, with no contention for all the other phrases that are being worked on, because they don't share anything in common. So it's a good question, and that's why, as you'll see, parallelism works best when we're in a situation where we have little or no, ideally no, dependencies between the various elements, and that's what leads to the so-called embarrassingly parallel model. So there are no sources of contention, or if there's sources of contention, they're not at the level of the data that's being processed. Okay. Another question that commonly comes up, we've talked about this before, is parallelism always a win? Will we always get a benefit of parallelism? The answer is no. And the reason for that is it really depends on how many elements there are. If we're only searching for, say, one phrase in one file in Shakespeare, we're not going to get a big win from parallelism. If we have lots of files, there's something like 37 or so plays of Shakespeare and a bunch of sonnets, that's a fairly good number. And if we have 100 phrases we're looking for, all of a sudden n gets big. So that's a win. Likewise, Q, which is this quantification of how long the processing takes for every piece of data, if it takes a while to search a work of Shakespeare to find out whether a phrase occurs, then of course, the longer the processing and the more data elements, the bigger the win of parallel processing, especially in situations where there's really no contention. So this is the kind of environment, this type of program that we're looking at here, the searching the streams to find phrases, text processing. That's a great example of something that scales up extremely well when you have large numbers of text strings or text files to analyze and a fair amount of processing for each of the different pieces you're looking at. Okay, so that's an end of comparing sequential streams with parallel streams. You'll get a lot more discussion of this down the road because this course is all about parallelism ultimately.